Okay, today we start a new chapter, chapter 4 in your textbook, which is the soil solution. This is extremely important chapter, so I will try to be very thorough and go slow so that you can understand everything. But please concentrate when you study the material and when you listen to this video or the many videos coming on this chapter. Soil solution represents the dominant site of chemical reactivity in soils. So that's where most of the reactions that will take place, most of the activities, anything chemical has to happen in the soil solution. It is the natural medium for plant growth. What do we mean by that? When we say it is the natural medium for plant growth, that means plants will take their nutrients from the soil solution. Plants will take only ions, and ions can be found only in soil solution. So that is the medium for plant growth. It represents the chemical fraction immediately available in the environment. What do we mean by these statements? It represents the chemical fraction immediately available in the environment. When we talk about the environment here, of course, we talk about something beyond the soil. So anything that has to go to the lower layers, to the sorry, to the underground water, it has to go through the soil solution. It has to go through the soil. So that's why it represents the chemical fraction of the soil, of course, immediately available in the environment. That's what the environment is in contact with as far as the soil is concerned. Emphasis on obtaining a model. Usually we try to understand the soil and especially the soil solution through models. Okay, what are the different types of models? Conceptual, they are based on certain concepts of the soil science. Experimental, they depend on experiments carried out by soil scientists and the data they obtain from these experiments. Or computational, that realistically represents soil solution in situ. Computational, that means using computers to model out from different data we have. So the major important thing we want about any model is that it should represent the soil solution in situ, in place, how it is, to describe the soil solution as it is in the soil system. Soil solution chemistry provides useful approaches to characterizing soil chemical processes of importance to agricultural and environmental sciences. So, sorry, soil solution chemistry provides useful approaches. How do we approach? Methods to characterizing soil chemical processes of importance to agricultural and environmental science. If you remember in chapter 1, we said, why do we call soil chemistry now environmental soil chemistry? Because it involves not only the agricultural aspect, but also the environmental science. We talked about the pollutants and how they can move, the different types, and how can they affect the environment, how can reach the uh, underground water, and affects eventually that's used by humans and animals. So that's the environment we are interested in. We do not talk here about the total environment, the air and this. No, we talk about the environment that's in contact with the soil, that has relationship with the soil. Okay, this diagram really explains how the soil solution is the center of all activities. Concentrate on all what we will see in this diagram. Dynamic equilibrium reactions. What do we mean by dynamic? That means they are not constant, they are not static, they move, they change all the time. So if you notice between any of these different rectangles, the arrows are two ways, which means into the solution and out of the solution. Let's look at these individually. The herbivores, plant uptake herbivores, of course, the ones that eat the plants, and the plants take their nutrients from the soil solution. And of course, when the plants decompose, eventually some of their constituents will go back into the soil solution at some point. Sorption. So again, sorption and the opposite of it, desorption. Okay, sorption and desorption, or it can be adsorption and also resorption, which when they leave. So that means that things can be taken from the soil solution to surfaces and to other things, and at the same time they can go back into the soil solution. Solid phases and minerals. This process is really equivalent to saying precipitation and dissolution of different compounds. This arrow, that means things, when they come out of the soil solution, they precipitate as compounds, so they become solid phases. If these solid phases, minerals, compounds dissolve again, their constituents, their ions, will go back into the soil solution. Here, the solute, transport, evaporation, and runoff. Of course, you can have leaching below the soil surface, way down from the soil solution. And then you can have evaporation to the atmosphere and losing moisture and other things that if they are volatile. So this is also in contact with way below and way above. And soil atmosphere, of course, we have the atmosphere inside the soil. It can be in equilibrium with the soil solution. So gases can be dissolved in the soil solution, and they can leave the soil solution and get back into the soil atmosphere. And some of them will volatilize. Volatilize, that means they will be lost to the atmosphere above the soil atmosphere. Sorry. Then we have the soil, organic matter, and microorganisms. Of course, sorry, any nutrients taken by the plants or by microorganisms, they will be part of the organic matter, which eventually will be in the soil. And when that decomposes again, it will release these constituents back into the soil solution. So you can see how the soil solution is the center of all activities that take place in the soil system. And here, the soil solution is composed of course, the aqueous phase, the water, plus the free ions. We will talk more about this, and the complex ions. So we have free ions and complex ions. Okay, assumptions to be met for soil solution chemistry to be useful. How can we utilize the chemistry of soil solution so that we can make use of it, so that it's so useful for us? First, soil solution represents the natural medium for plant growth. We just said that. Then, prediction of plant response to chemicals occurring in the soil environment. So, it is the natural medium where plants absorb their nutrients from the soil solution. And then also we can predict how do plant response to the different chemicals which occur in the soil environment. Some of these could be insecticides, pesticides, any other chemicals used by the humans, how the plant respond to that. Second, salt solution can be related to mobile water in the soil environment. Then predict the forms and amounts of chemicals that may reach ground and surface water. Okay, we'll read it again. Second, soil solution can be related to mobile water in the soil environment, the water that is moving all the time in the soil environment. And of course, that water is not really pure water. Remember, it's the soil solution, the water and all what is dissolved and suspended in it. Then we can predict the forms and amounts of chemicals that may reach the ground and surface water. If we understand the chemistry of salt solution, then we can also predict the chemicals that could reach the groundwater or the surface water. Surface water here we mean lakes, rivers, oceans, wherever all of these are bodies of water on the surface. Third, salt solution approaches a steady state relative to the soil solid state or solid phase. Predict solid phase components controlling chemical distribution in soil. Okay, so salt solution approaches a steady state. The meaning of a steady state, the same as we are saying equilibrium. So when we say the salt solution approaches a steady state, it approaches equilibrium relative to the soil solid phase. So it becomes in equilibrium. You remember in that diagram we saw the arrows back and forth. So that indicates the reactions go in the two directions. So when we have an equilibrium, then with the solid phase, that's a steady state. So then we can predict solid phase components controlling chemical distribution in soil. Then we will know from this that steady state or the equilibrium, we can tell what are the compounds of each element that are important in controlling the chemical distribution of these elements in the soil. Many of these ideas will become clearer as we go more and deeper into this chapter. So remember, just sometime you might have to read the same idea several times so that you can understand it. But I will try to explain every one of these ideas as much as I can, even though we are not close, so that I can explain it for you better, but I will do my best. Fourth, salt solution composition controls bioavailability to soil microbes, provides information as to the concurrent processes of sorption and metabolism. So, salt solution composition controls bioavailability to soil microbes and also to plants too, not only to microbes, but the availability to any living things, the soil microbes as well as the plants, of course, which absorb through their roots from the salt solution the requirements, their nutrient requirements. And it provides information as to the concurrent processes of sorption and metabolism. So concurrent things that happen at the same time. When we say these are concurrent processes, that means these processes happen at the same time. They are taking place at the same time. Sorption by the bio, which means the living things, so they can take these nutrients or elements from the salt solution, and then they go into the bodies of these living things in the form of metabolism to form different types of compounds within the living things. Now, measurement of the salt solution. How do we measure? We will go into, again, detail. How do we measure the salt solution and measure its characteristics? Intensity factor. First, we would need to learn about two very important terms. The first one, the intensity factor of an ion, its concentration in the salt solution. So when we say the intensity factor of any element ion, that means how much of it is in salt solution at that time when we take the sample, when we measure it, when we determine it, how much of it now. That's its concentration in the salt solution. Then we have the capacity factor of an ion, which is the ability of solid components in salt to resupply the ion when depleted from the salt solution. So if we have a certain ion, let's talk, say, about potassium ion, K+, okay, that can be taken by plants, by microbes. So it will be taken away from the salt solution. So that concentration, which is the intensity factor, will be reduced a lot. So it comes to the point of depletion. What does depletion means? Went down to very low amounts. It depleted, almost nothing is there. Then you have to resupply. If the plants have to live, the microbes have to live, you have to resupply this ion. How is it resupplied? Through the components, solid components of the salt. So if they are minerals, they will dissolve, or compounds of that element, where they will dissolve to give that element again in the salt solution and raise its concentration, its intensity factor. If it's organic compounds, they will decompose, they will mineralize to release that ion into the salt solution again. So that is why we said the ability of these solid components can be inorganic or organic to resupply that depleted amount of that nutrient. And we can talk about this for every ion that the plants take. The measurement of the intensity factor is critical in predicting and understanding reactions in the soil environment. The actual intensity factor, which is its concentration at that time, is extremely important because that is the part that's available for any kind of reaction. Until resupply comes later, but that part of it, the intensity factor, the concentration of an element, is what is involved in any process that takes place in the soil. So it makes it in predicting and understanding reaction in the soil environment. Like what? Like weathering. The weathering process, of course, here we talk about the chemical weathering, which are taking place all the time. Bioavailability, how available it is to the living things, to the microbes and plants. Mobility, of course, if there is any mobility, it has to be the ionic form, the intensity factor, the concentration which is now there. That is the one that's going to be mobile and moving through with the water and going down. Geochemical cycling. Geochemical cycling, this is extremely important phenomenon and process that we should understand, because that's what really connects the soil with the environment and the soil solution with the environment. We said geochemical cycling. Geo, when you hear the word geo, immediately most of you, I hope, will come to his mind the geology. So we're talking about the deeper layers way below the soil. So what do we mean by geochemical cycling? Okay, if you have a nutrient and it was leached down, left the salt solution because it's mobile, and it reached the groundwater. The groundwater, where are they? They are in aquifers. They are part of the geology beneath the soil. So they become part of the aquifer, the soil, way below the soil. They are the aquifers that hold the underground water, the groundwater. Okay, eventually that water humans will use. They will pump them and they utilize them for animals, for humans, for irrigation of plants. So we are using them. After we use them, those nutrients that are in them can be utilized by the human, by the animal, by the plant. And eventually, if they are utilized by a plant or an animal, they could be in residues again on top of the soil, in that those residues will decompose, and then we release that nutrient again. Then it will leach again down. So we have a cycle. See what we mean by cycle? So it finished its cycle, started from the soil, went down to the underground, pumped again, used, released again, and it came back to the starting point. So that is cycling. The measurement of soil solution components in situ is very difficult and technically not possible. So even though the advances of science are far really advanced now, we have very good advancement in science, and yet we can never measure the soil components, the soil solution components. What are the components? What are the nutrients? What are the elements? What are all the ions that are in the soil solution in situ, where they are in the soil? We cannot measure them there. So it's very difficult, and technically, from a technical point of view, it's not possible. So we cannot measure what the soil solution contains while it is in the soil. In other words, we cannot push in some instrument inside the soil solution and that machine will tell us exactly what's there. We cannot do that. This is not available. So what do we do then? How do we study the soil solution? We have to bring it to the laboratory. So we will talk about laboratory methods used to obtain samples of the soil solution. So we have to find a way to bring samples of that soil solution, bring them to the lab. Then it's easy to determine all what it has. When we have it as a sample in the laboratory, we have all the equipment, all the procedures, all the chemistry we need to know how to analyze and how to find the components of soil solutions. So we classify those methods of how to obtain samples of the soil solution into different classes or different methods. First, displacement techniques, including column displacement. Unfortunately, if we were in the class, I would draw to you some diagrams and show you how it happens. And hopefully someday we will be able to do that. But to displace it, in other words, we put soil which is in field capacity in a glass column, like a cylinder. We pack the soil there, then we put a solution on top. That solution pushes the soil solution down, and we collect it from the bottom using like a burette type control, and we collect it and then analyze it. Simply, in simple words, that's how it works. Then we have centrifugation. Centrifugation, of course, you bring the soil solution, the soil that has soil solution part of it, and you centrifuge that sample and you get out soil solution. You separate it from the soil. And then we have saturation extract. Saturation extracts, these are usually part of the studies of saline soils. So the saturation extract, you prepare what we call a saturated paste. I am sure you will cover it in some other courses. I'm sure maybe Dr. Mamoun will cover it in some of his courses. So you prepare a saturated paste, and then by suction, you obtain the solution from that saturated paste. And what you get is what we call saturation extract. Okay, the amount of water a saturation extract is about double the field capacity. That's why they chose it. So we can relate the concentration of ions in the saturation extract to the field capacity, which is our ideal. Our ideal condition for soil solution is the field capacity, when the moisture is the optimum for plant growth. But this one has more moisture, but it is double. So the concentration in this extract will be half the concentration in the field capacity extract. So that's why we can use this and relate it to the optimum we need. The column displacement method is probably the most reliable method for obtaining a sample of the soil solution. First one we described it briefly is the best one. It's the most reliable, the best one to represent the soil solution in the soil. But this procedure is tedious. It's difficult, hard to do. It's not an easy thing and very time consuming. When we put a dash or hyphen between time consuming, one meaning, that means it takes too long. So it takes long time to do and lots of effort. That's why people do it only for research. Usually you don't do it for routine analysis to obtain soil solution samples to study for practical things, only for research. Centrifugation methods are the most widely used because they are relatively simple. These are the simplest, fast, and cheap because you find centrifuges in almost all laboratories. They're not very expensive instruments. So this is simple thing, fast, and that's why it's the one that's used by most scientists and by most people who want to study the salt solution in the laboratory. Okay, now we turn into the study of the salt solution itself. We said we obtained it. We learned how to obtain a salt solution. We brought it to the lab. We analyzed. So how do we go about studying that salt solution and its solutes? It solutes everything that is in the soil solution. The solutes, remember, solute and solvent, we studied at the beginning of the course. Solute is what dissolves in the solvent. Our solvent here is water. Salt solution is an aqueous system, and all solutes, everything that is dissolved in it. The salt solution is defined as the aqueous liquid phase of the soil and its solutes. So, like I said, and you should always remember, we never have soil water, pure water. You can never have, although we talk in physics, soil physics, I think they concentrate on the movement of water and all that. But for us in chemistry, that water is not water. It's a soil solution because it has all the constituents, all the solutes that are dissolved in it as part of it. And it's the aqueous liquid phase of the soil. The majority of solutes in the soil solution are ions, which occur either as free hydrated ions. So how do we find what are the forms that we can find all these ions in, the one that exists in the soil solution? First, they can be free, but free here we have to add to it hydrated because they are in water, in aqueous system. There is always a group of water molecules surrounding that ion. They are water molecules surrounding that ion. So we have aluminum 3. You don't find aluminum 3 alone. It will be hydrated. It is free ion, but it has water molecules. They do not change its valence. They do not change its chemistry very much. So they just surround it. So Al, because they're attracted to it. Remember, water is polar compound. So it surrounds any charged ion. So we have aluminum with 6 water molecules, H2O 6. The valence, of course, will stay the same. Trivalent aluminum still will be trivalent hydrated aluminum with 6 water molecules surrounding it. As various, so the majority of solutes are ions which occur either. Either means either or, means more than one thing. So either the first one is the free hydrated ions, or the second as various complexes with organic or inorganic ligands. Ligands, any negative thing. Remember, the cation, sorry, the cations will have ligands surrounding them, attached to them. Okay, so you have complexes. Complexes, that's a reaction to form a complex. And that complex from the ion with an organic or inorganic ligand. Okay. Inner sphere complexes. No water molecules are present between the metal ion and the ligand. So when we say inner spheres, so here we talked about, remember, free ions, nothing, the water molecules are not considered complexes at all. Don't think about them as complexes. Complexes have to be with either organic or inorganic ligands, negative things that surround the cation or the heavy metal. So inner sphere complexes, this type of complexes, when no water molecules are present between the metal ion and the ligand. So the ligand and the metal are in contact, immediately in contact. No water molecules separate them at all. And then we have the second type of complexes, which is the outer sphere complexes, when a water molecule is positioned between the metal ion and the ligand. So in that case, there is not immediate contact between the metal and the ligand. There is a water molecule that's surrounding that metal and pushes away the ligand from that metal. So there is water molecules separating them. So that's why it's called outer. The inner next to it, nothing separating them. It's easy to remember, easy to know the difference. Outer sphere complexes are not as tightly bound as inner sphere complexes. Of course, the outer sphere, there is water molecule that separates them from each other. So they are not as tightly bound as the inner sphere complexes. That's clear and easy to understand. An uncharged outer sphere complex is often referred to as an ion pair. Example, calcium divalent plus sulfate divalent ions are known to form ion pairs. So we have CaSO4 0, although it has no charge, and yet it's called an ion pair. Ion pair because there are two ions that got together to form an ion pair. So this is not a solid. This is not a compound that precipitates. This is still soluble and is still part of the ionic forms of those two ions, calcium and sulfate, but it has zero because divalent, two negative, two positive. That means it has zero charge. So we put the zero to indicate that it is an ion, not a solid. If it was a solid, we will not put the zero. If we put the zero, it's an ion pair. The speciation of the salt solution refers to determining the distribution of ions in their various chemical forms. Okay, this is extremely important. We're going to work on it from here for near most of the chapter to talk about the speciation of the salt solution. It refers to determining the distribution of ions in their various chemical forms. We will see, say, if we talk about calcium, what are the different chemical forms that calcium can exist in? One of them is this. This is the free ion, Ca2 plus. This is an ion pair. It can also, sorry, it can form also with complexes with other ligands like chloride, like bicarbonate, like many others. So these are all, each one of them is a different species, different form. So the speciation is a process to find the different species. Species are the individual forms. Speciation is the process to determine what are all the different species of that ion in salt solution. So determining the distribution of ions in their various chemical forms. Total ion concentration is the sum of free and complex, and remember, that's what we said. Any ion will be either in its free hydrated form or as complexes. So the total ion concentration, which is the sum when you add all the free and all the complexes, the free is 1, but all the complexes, add them to the free form of the soil solution, is measured by analytical techniques and provides information. So the total ion concentration, if you determine any ion by any analytical method, by say colorimetry, by precipitation, gravimetry, HPLC, by atomic absorption, whatever procedure you use, that value you obtain is what we call the total ion concentration. It does not differentiate between the different forms. So that total ion concentration is the sum. It's all of them together, the sum of the free and complex ions. It does not differentiate between these. So this is our purpose. In this chapter, we'll see how can we then find from this total the different forms, the different species of that ion in the salt solution. So the total ion concentration is measured by analytical techniques in the laboratory, and it provides information. What do we get? What kind of information we obtain from this total ion concentration? Why do people run these elements, determine the amounts of these elements, their total amount, their total concentration in the salt solution by analytical methods? What information we get out of that? First, quantities of ions available for plant uptake. So remember, we said that is the intensity factor. It tells you how much of that ion is available for plants to take right away. Movement through the salt solution. We said that the mobile form have to be the ionic. So that intensity factor, the amount, the concentration that's already there, that's also what's available for movement through the soil profile down, and it could reach, down to the soil profile, from the soil profile down to the groundwater. It is important that the speciation or chemical forms of the free and complex ions be known. It is important that the speciation or chemical forms of the free and complex ions be known. It's not enough for us to know this, although we said it's very useful. We learn many things from this total concentration. But to understand the chemistry of salt solution, to understand what's happening there, we need to know all these complexes. We need to know how much free form and how many complexes and what's their concentrations. Okay, due to what causes these these complexes to form? We have many reactions that take place. We have hydrolysis, complexation, reduction, oxidation reactions. All of them form different complexes. The general hydrolysis reaction for a hydrated metal, MH2OX, M+. Okay, please concentrate. Usually, when we use these symbols in many exams, I will ask the same exact this reaction, but I will give you different symbols and the students get lost. That means you really don't understand what's happening. Concentrate on what I'm saying now. So it doesn't matter what are the symbols you see here, no matter how they are changed, the idea will never change. It's the same. So we're taking a metal with with water molecules surrounding it, water of hydration, remember? So this is free hydrated ion. Okay, the number of water molecules surrounding it, X, Remember, in the aluminum case, we saw Al3 plus, H2O6, and this is 3 plus. That's an example. But we put it in the general form so you can have it for any ion, aluminum or any other ion, it will be the same behavior. So M is for the metal, for any ion, which has probably positive, if not probably, it has positive charge. It's a cation surrounded by water molecules. The number of molecules in this case, we call them X. And the charge of that, N plus. Say if it was aluminum, this will be 3 plus. If it's any other divalent, it will be 2 plus. If it's 4, it'll be 4 plus. So this N is an integer which changes according to what is M. So let's take what happens, the hydrolysis. Remember hydrolysis, the reaction with water. So M H2OX to the power, not to the power, the charge is N plus. So we have M surrounded by X water molecules, and the charge of that metal is N plus. Okay, it's now going to hydrolyze. Since it's a positive cation, it's going to attract to it hydroxide, OH groups. So we are saying here that the M took OH, the number of those OH is Y. So it became MOHY. Sorry. Okay. Generally, this X is a number that's particular for that element, and usually it goes with its coordination number. Remember, we learned the coordination number earlier in the course when we talked about Pauling rules and all that. So this X is kind of fixed number for that metal. So remember, for aluminum, it was 6. So this X is its coordination number, the number of water molecules that surround it. So now, OH, the number of OH that this metal attracted is Y. Okay, this Y replaced some of the X's, right? We have XH2O. Some of this X, this number, was replaced by certain number of OH, and that number is Y. So how many H2O remains? X minus Y. So we have X H2O, Y OHs came into place, attached to this, and they took the place of the same number of H2O. So the number of H2O remaining will be X minus this Y, this number. Okay, now each OH carries one negative charge, right? So the N plus will not stay N plus because now we have OHs and their number is Y, and each one of them carries a negative charge. So the total charge of this complex now, N minus Y, positive charges. N, and we subtracted from it the number of OHs. Each one of them has a negative charge. So N minus Y. Remember, we put these in parentheses and we put the positive charge. The positive charge is for this number. N minus 1 becomes a new number instead of N minus 1 between parentheses plus. Plus, of course, if we have Y OHs attached, Y OHs attached to M, where they come from? They come from H2O molecules. So they have to be H's, the same number released, plus Y H plus Y H plus hydrogen, okay? So make sure that I usually the students put sigma. I don't know if your textbook, I haven't looked at your textbook lately. If this number, anything other than this, something's wrong. This should be always the same. If you put Y here, this has to be Y. If you put M here, this has to be M here, whatever it is. So no other value, no other form of any letter can be other than the same that we used for the OH. So the number of OH here, Y, so the same hydrogen number will be released to give you YH plus, okay? Okay, now we talk about a general complexation reaction between a hydrated metal, which is MH2OX N plus, the same one we used in the previous slide, and a ligand, L we named it, that carries L negative charges, small l, the charges of L, okay? This complex of the metal with the hydrogen, sorry, with the water molecule surrounding it, the hydration water surrounding it in N plus, that's its original valence. And this one has the valence of L minus to form an outer sphere complex. Remember, outer sphere, because we have here water molecules. So the water molecules will be separating the M from the ligand. They are not in contact. They cannot be an inner sphere. So A of this plus B of L, which carries L minus charges, give us M H2O X A, because we have A of them, L, we have B of them, just like you form any compound. Just think of, like you say, potassium plus sulfate, potassium plus sulfate, and you obtain K2 and so forth. Same type of thing, just we put it in general so that it applies to any type of reaction you write. A and B, we call them stoichiometric coefficient. Stoichiometric coefficient. A and B are stoichiometric to balance the equation. Remember, we always multiply the different parts of an equation, chemical equation, to balance. You have to balance the number of atoms on the left side has to equal the number of atoms on the right side. The number of charges, their quality, their type and number on the left has to be equal here also. So that's why we call them A and B, the stoichiometric, the balancing factors or coefficients. Analytically, it's not possible to determine all individual ion species that can occur in salt solution. We already said that. It is not possible to determine all the individual ion species that can occur in salt solutions. To speciate the salt solution, one must apply ion association or speciation models using the total concentration data for each metal and ligand in the salt solution. So that's why we said, because we cannot determine, we have to use certain type of models. We have to use our knowledge about salt chemistry. We have to use our experimentation. All of this combined to find the speciation we are interested in. Okay, I'm gonna stop here. Today we can